Hello. In the previous video lecture, we started talking about a goal programming approach, and we said that sometimes the constraints, the restrictions in the real life are not too hard. We want to satisfy those restrictions as much as possible, but still we are allowed to exceed them. And if we exceed those restrictions, then we want the deviation from that target value to be as minimum as possible. So if we have such situations, then we call such constraints as soft constraints. And in goal programming approach, we write those soft constraints as objectives. And the regular restrictions, if we are not allowed to exceed, if we have to satisfy those restrictions, there is no way to not satisfy those, then they are called hard constraints, and they still appear as they are in our models. Okay? So in today's video lecture, we will make another example to write a given problem as a goal programming approach, model as a goal program, and then we will learn how we can solve these goal programming formulations, because if you remember the previous example, the final formulation appeared to have more than one objective functions. So if you have 2 or 3 objective functions, how you can solve it? For example, using Cplex, because Cplex will not allow you to write more than one constraint. Then you need to be able to somehow convert it to a single objective and solve it. So we will learn the idea behind this multi-objective optimization and how we can solve it. Basically, in this video lecture, we will talk about the weighting method. So let's get started. Okay, we have such an expansion. So there is a convention center at an hotel. Okay, and we want to expand this convention center by adding more conference rooms. And there are 3 types of conference rooms that you can include. Either it can be a small one. The small one has a size of 400 square feet. And if you want to establish one small conference room, and the total cost is this much. Again, for medium, the size and the cost is given, and for large, the size and the cost is given. So there are 3 alternative types of conference rooms. And the thing is, we would like to add 5 small conference rooms, 10 medium, and 15 large conference rooms. And we want the total expansion to be 25,000 square feet. So you see, these are the area requirements of the small, medium, and large conference rooms. And when you add these numbers of conference rooms, we want this total expansion to be 25,000 square feet. And the cost of the project should not exceed $1 million. So individual costs of the conference rooms are given, and we don't want them to exceed this. So every data given here, for example, this one, we want to include 5 small conference rooms. The thing is, this is a soft constraint. We want to include 5, but it can be 4, it can be 6, it can be 7. Similarly, our target value for medium conference rooms is 10, but still we can deviate from it. And the thing is, we want to minimize the deviation. Still, also for the size and for the budget, we can also deviate from these, and we want to deviate as small as possible. Okay, this is the problem, and the thing is, these deviations can be positive or negative. In some cases, we don't like positive deviation. In some cases, we don't like negative deviation. For example, for this area requirement, we don't want to exceed, or we don't want to exceed this value, or for the budget we don't want to exceed this value, so positive deviation is a problem here. But when we come to this conference rooms, okay, we want to add 5 small conference rooms. If you include 4, which means less number of conference rooms, then we don't want to have less conference rooms. Okay, negative deviation is problematic there. So keeping these in mind, let's first write these constraints and then convert them to goal programming formulations. Of course, first thing is to define our decision variables, and you should ask yourself what we are trying to decide on. And the answer is, in fact, we are trying to decide on the numbers of small, medium, and large conference rooms. So x1 represents the number of small rooms, x2 represents the medium, and x3 represents the number of large rooms that we are going to add. Now, using these decision variables, we will write the constraints. So for us, the given constraints or restrictions can be represented as these 5 goals. So what are these goals? The first goal is we want to include 5 small conference rooms, but if we include more than 5, it's okay. But less than 5, we want to restrict it. We want to stick to 5 as much as possible. So being less than 5 is problematic for us, not being more than 5. But of course, if you think that being more than 5 is also problematic, then you can formulate it in that way. In that case, you should say, okay, the number of small rooms must be equal to 5, or should be equal to 5 as much as possible. But in this example, we assume that if you exceed that number, that's okay. But if you are below that number, then we don't want it and we want to penalize it. That's why we represent our first goal as the expansion should include at least 5 small conference rooms. In goal 2, similarly, the medium conference rooms should be at least 10. And in goal 3, the large conference rooms should be at least 15. These are the first 3 conference rooms, first 3 goals related to the number of small, medium, and large conference rooms. In goal 4, we want the expansion to be 25,000 square feet. So in order to show you different aspects of the goal programming, now we assume that we want to stick to this 25,000 as much as possible. We neither want to be less than that value nor to be greater than that value. Okay, we want to be equal to that value. That's why we represent goal 4 as the expansion should consist of approximately this square feet, and we both penalize the negative and positive deviations. And finally, for goal 5, we have a budget of $1 million. If we are less than this, we would be happy. But if the total project spendings is larger than this, then we want to penalize it. That's why we represent it as the expansion should cost at most $1 million. With these statements, now we can represent these as constraints in the following way. Okay, we want x1, x2, and x3, the number of small, medium, and large rooms, to be greater than or equal to the given target values. Okay, we want x1 to be greater than or equal to 5, x2 greater than or equal to 10, and x3 greater than or equal to 15. The total square feet of the project should be equal to the target value. So this is the size of one small room multiplied by the number of small rooms. Size of the medium rooms, conference rooms, multiplied by the number of medium conference rooms, and etc. This is the total area requirement of the project, and we want it to be equal to our target value. And for the cost, so the cost of establishing one small room was 18,000. So we just ignored the 1,000 part all over this constraint. So 18 times x1, the number of small conference rooms, 33 times x2, and 45.15 times x3. We want this to be less than or equal to our budget. Okay, but as we said, if you write these into your Cplex model, as we learned already as it is, then they are called hard constraints, and Cplex will try to satisfy all of them. But the thing is, we are allowed to exceed, or we are allowed to deviate from these target values. Therefore, we need to use goal programming. As we said previously, while representing those constraints, soft constraints, as goals and constraints in goal programming, we include deviational variables. For each constraint, we need to include two variables. Okay, so in the previous example, we used S to represent these. In this example, we are using D. It's just the notation, it doesn't matter. Okay, so for the first constraint, what do? We include one negative deviational variable with a plus sign and one positive deviational variable with a negative sign. Again, I'm repeating, these negative and positive signs are just notation at the, superscripts. They are just notation. They don't mean anything, but they just define you that this variable d1 minus is the negative deviation. It means that you are below your target level, and this says that you are above your target level, and depending on what you want to do, you will penalize one of them or both of them. Okay, so the first one, we say that okay, x1 plus negative deviation minus positive deviation will be equal to 5. So all goal programming constraints will be equality constraints. For medium rooms, again, we include the two deviational variables, and for large rooms, we include the three deviational variables. Okay, these are the first three constraints. We do the same thing for the last two constraints. For the area requirement, again, we include two deviational variables and this was already equation, and don't forget, even if the constraint is equation, we still include these deviational variables. Okay, and always, again, so the most common mistakes that the students do is to write these deviational variables with wrong signs here. Either they write all of them as a plus sign or minus sign. So negative deviational variable should appear with a plus sign, and positive deviational variable should appear with a negative sign. And again, for the total cost, similarly, we include the 5 deviational variables. Okay, so these 5 constraints are now converted into goal programming constraints. After writing these goal programming constraints, then what are our goals? What we try to do? Remember, we want to have at least 5 small-sized rooms, conference rooms, at least 5. Okay, so what does it mean? We want to minimize the negative deviation, right? If we are larger than 5, we are perfectly fine. But if we are less than 5, we don't want it. That's why our first goal is to minimize the negative deviation. Similarly, for medium and large conference rooms, we want to minimize the negative deviation. What about the area requirement? We want to be equal to, we want the project size or area to be equal to 25,000. Okay, so it means that we want to penalize both the negative and the positive deviations. Therefore, for our fourth goal, we write minimize the negative deviation plus the positive deviation. And if we write in this way, we say that negative deviation and positive deviation are equally important. What does it mean? It means this. So our target level is 25,000. Okay, let me write 25. So if you are one less from this, it means that in the optimal solution, if you are 24, which means that the deviation is 1 unit. This is exactly as the same as having a solution with 26, which means that the deviation is 1 unit. This is positive deviation. You exceed the area requirement by 1 unit. This is negative deviation. You have less than the target level by 1 unit. And when you just add up these two values as it is, you assume that negative deviation is exactly equal important than the positive deviation. But sometimes one of them is more valuable, more important than the other one. For example, you don't want positive deviation, still it's allowed, but you don't want it, and you don't want negative deviation as well, but positive deviation is worse than the negative deviation for you. If that is the case, then what you can do is for this problem, you can say that, okay, positive deviation is 2 times, for example, important than the negative deviation. So you multiply it by 2. Or if you believe that it is not 2 times more important, but it is 5 times more important, then you multiply it by 5. It means that you are multiplying this deviation with a weight, and if you multiply one of them with a weight, it means that this positive deviation is 5 times more important than this negative deviation. Okay? This weight, the magnitude of that weight gives you the level of importance. Of course, how do you know this positive deviations is this much important than the negative deviation? It's very difficult to quantify. The thing is, there is a decision maker. There is the person who wants this design, who wants this project. And this is his decision. He needs to answer this question, not you. We are just the optimizers. We are just the operations research scientists. And we want to achieve what this decision maker wants. Okay, so that's why these numbers should come from the decision maker. Okay, so if they are equally important, we just add them. If one of them is more important than the other one, then we include a weight in front of that one. Okay, and the last one is the budget constraint. And for the budget, we don't want to exceed $1 million, which means that we are penalizing the positive deviation. Okay, so now these are the 5 goals of the problem. Now we have the constraints and we have the goals. The thing is how we can solve and how we can find the solution. Now let's concentrate on that part. For solving goal programs with these more than one such objectives, we will learn basically 2 methods here. The first one will be the weights method, and the second one will be the preemptive method. In fact, for multi-criteria optimization, there is a large theory behind it. There are other different methods that you can use for multi-criteria optimization problems. But here in this video lecture, we will just concentrate on these 2 methods. Okay, so we will start with the weights method. Let's see how we can solve using this method. So before understanding this weighting method, we should understand something about the objectives and about the solutions to these multi-objective optimization problems. So let's consider 2 solutions to the given problem. Let's assume that in one of these solutions, we found that let's only just concentrate on 2 of the objectives. Let's forget about the other remaining 3, but let's just concentrate on the number of small rooms and the total cost. Okay, just these 2 objectives, and assume that in the first solution we found that a solution with 4 small rooms and with a total cost of 900,000. So that solution in this graph, I represented it. So this axis shows the cost. So this is 900,000. Okay, and this axis represents the number of smaller conference rooms, and this is 4 rooms. Okay, so solution 1 on this graph represents this dot, and solution 2, 5 small rooms, and the cost is 1,100,000, 1.1 million. Okay, so this solution is represented with this one here, 5 conference rooms and 1.1 million cost. Now the question is, which of these solutions is a better alternative? So please think on this. Which of these solutions will you prefer and why? And remember what we try to achieve. We try to achieve at least 5 small conference rooms, at least 5. And we want to achieve at most 1 million cost. Okay? So when you compare these two solutions, which of these two solutions is better? Okay, so be careful in your reasoning. In solution 1, the cost is less than solution 2. So therefore, if we just look at the cost side, we prefer solution 1, right? But when you look at the number of conference rooms, and the second one has 5 conference rooms, which was our target, and the first one has 4, which is less than our target. And with respect to the number of conference rooms, we prefer solution 2. Okay, so with respect to one objective, we prefer one solution, and with respect to the other objective, we prefer the other solution. So if we have such two solutions, we call these solutions as non-dominating solutions. Okay, so these two solutions does not dominate each other, and we are indifferent between these two solutions. Okay, we are indifferent. And the thing is, as an operational researcher, we are not the one who will make this decision. The decision maker will tell the answer. We will ask to him, okay, we have such two solutions, which one will you prefer? Then the decision maker will tell, okay, I prefer this solution because of this reason. He will select the solution. Okay, our task is to generate all such solutions. And the thing is, if we have a multi-criteria optimization problem with conflicting objectives, which means that if you minimize one objective, it leads to the minimum solution for the other objective, then these two objectives are not conflicting. But if you have two objectives such that in order to improve one objective, the other one is sacrificed, the other one becomes worse, then these two objectives are conflicting objectives. And in many cases, we have conflicting objectives in real life, and if that's the case, we cannot talk about a single optimum solution. Okay, there is no single optimum solution for such optimization problems. But what do we have is, we have a set of such indifferent solutions, or we call them efficient solutions or Pareto optimal solutions. So I will not go into details of this discussion. It's another topic. But the thing is, you need to understand that there are solutions in multi-criteria optimization such that we are indifferent between these alternative solutions. In order to understand better, let's consider another example. So this time, again, we have these two solutions. Solution 1 has 4 small rooms and with this cost. And solution 2 has 3 small rooms and with this cost. Again, we can represent these solution 1 and solution 2 in our graph. Okay. So solution 1, the cost, solution 2, its cost, and when we compare these two costs with each other, we say that solution 1 is better than solution 2 in terms of cost. Now let's compare the number of smaller rooms. Solution 1 has 4, solution 2 has 3, and we want to have at least 5. We don't want these number of conference rooms to be less than 5. And we see that solution 1 deviates only 1 from our target value, whereas solution 2 deviates by 2 units. So with respect to this, also solution 1 is better than solution 2. If we have such a situation, then we say that solution 2 is dominated. It is not an alternative anymore. Solution 1 is better than solution 2 with respect to both objectives. We are not indifferent for these two solutions. We just prefer solution 1 over solution 2 in such a case. Okay, so this is the preferred answer for this case. So when we have multi-criteria optimization, we may have different solutions. Some of these solutions we may be indifferent between each other, but when we compare some of these solutions, we will prefer one of them to the other one, and the preferred alternative we will continue with. The other alternatives we just ignore. They are called dominated solutions. As I said, one method to find the solutions with multi-criteria optimization is to use weights. And by using these weights, we minimize those multiple objectives. We reduce those multiple objectives into a single. We combine them into a single objective. Remember, in our example, we had 5 goals, right? G1, G2, G3 up to G5. So in a general model, we may have up to n such goals. And we cannot use them in Cplex as separate goals. Minimize G1, minimize G2. It's not possible. Then one way is to combine these goals into a single objective. But the thing is, remember, our goal 1 was the number of smaller rooms, right? Number of smaller rooms. The number is 4, 5, and etc. And remember the last one, which was goal 5, it was the budget. And it is cost, and it's in terms of hundreds and thousands of dollars. So 1 million, our target level. The target level here was only 5, and the target level here was 1 million. Okay? So if you add these two to just as it is, G1 plus G5. So this 5 is a very smaller number when you compare to this 1 million. So it means that the Cplex will try to give more priority to this G5. So it means that if the units are different, they are apples and oranges. You cannot just sum them up. And for one of the reasons is this, and the other reason is the decision maker may have preferences. Even, for example, we consider G1 the number of smaller rooms, and let's say 3 the number of larger rooms. The decision maker may say that satisfying the restriction on the larger rooms is more important than satisfying the restriction on the smaller rooms. So if that is the case, you cannot just add these two goals as they are, but what do? You give a priority to this G3 by assigning a weight. That's why, while combining these multiple objectives into a single one, we multiply them with weights. Okay? W1 is the weight of the first objective, W2 is the weight of the second, and Wn is the weight of the end objective. We basically multiply the goals with these weights and sum them up. So now this is a single objective, and when we solve it, you will come up with a single solution. And how do we find these weights? And that's one of the most difficult parts in goal programming, and one of the most important parts, because the solution that you will obtain at the end depends on these weights. If you use as a weight, for example, if you use 1 here, 2 here, let's say 100 here, you will end up with a solution. But if you use another set of weights, for example 5 here, 1 here, and let's say 20 here, you may end up with a different solution. And when you compare these two solutions with each other, as I explained before, you may be indifferent between these two. In terms of one of the objectives, one solution is better than the other one. In terms of the other objective, now the opposite, the other objective is better. So which one will you prefer? So these objectives are very important, and you should get these weights. From the decision maker. So when we are talking about multi-criteria or multi-objective optimization, so interchangeably we can use these names: multi-criteria optimization, multi-objective optimization. Okay. So when we have such a formulation or such a problem, then we should talk about the decision maker. Decision maker is important, and these weights represent the preferences of the decision maker. In order to understand goal programming and different aspects related to goal programming, as well as this weighting method better, let's consider another example. So in this example, there is an advertising agency with 10 employees. Okay. And this agency has received a new contract to promote a new product. And this new product will be promoted through radio and TV. And for each one of these, we are given the necessary data. The number of people reached by each type of advertisement, so it's the exposure, is given. Per 1 minute of radio advertisement, okay, we reach 4 million persons. If we make a 1 minute TV advertisement, we reach 8 million persons. Similarly, for 1 minute of radio advertisement, the cost is $8,000, and 1 minute of TV advertisement is $24,000. Lastly, 1 minute of radio advertisement requires 1 employee, and 1 minute of TV advertisement requires 2 employees. Okay, so these are the given data. By the way, some of these constraints are defined as hard constraints that you cannot exceed. For example, these 10 employees, you cannot exceed, you cannot use more than 10 employees. It's a hard constraint. But some of them are soft constraints. So we want to reach these number of persons, and we want to have the budget in a target level, so they are soft constraints. So let's see what are those target values. Okay, so the limitations are this. Besides the number of employees, this is also a hard constraint given to us as a hard constraint. What does it mean? It means that the radio advertisement cannot be larger than 6 minutes. Again, I'm repeating, this is given as a hard constraint. You cannot, you have to satisfy this. Okay. On the other hand, these two are given as soft constraints. The first one says that TV and radio advertisements need to reach at least 45 million people. But this is a soft constraint again. And the available budget should be around $100,000. Okay, again, this is a soft constraint. Then the question is to decide on how many minutes of radio and TV advertisements to use. So we will first define our variables and we will write constraints. So at this moment, please stop the video and try to write these by yourself. Okay, please spend time on it, and then I will show you how to model it. Okay, I hope you worked on this example by yourself. And now let's see the solution, how to model it. Let's first start with the constraints. We had two hard constraints. The first one of the hard constraints was the personal limitation. Okay, so we had 10 employees and we cannot exceed. Of course, before that we need to define our decisions. What should be our decisions? Let's first start from there. The question was this: how many minutes of radio and TV advertisements you need to use? Therefore, we need to define two decision variables, x1 and x2. So x1 will represent the radio minutes, number of minutes of advertisement in radio, and x2 represents TV. Okay, so using this, let's try to write the first constraint, which is the personal limit. And the personal limit is, for 1 minute of radio advertisement, we used 1 employee. So 1 times x1. And for 1 minute of TV advertisement, we require 2 employees. So in total, 1 times x1 plus 2 times x2 is the total number of employees that we require. And this number should be less than or equal to our required number. And as I said, this is a hard constraint. And when we have hard constraints, we do not convert it to goal programming formulation. We are not adding these deviational variables. We are not converting it to equality. We keep it as it is. So this is our hard constraint. For the second one, hard constraint, we have this radio limitation. The total number of minutes in radio advertisement cannot be more than 6. Okay, so basically the constraint is x1 less than or equal to 6, and again we do not convert these to goal programming constraints. Now let's consider the other two. The first of these is the exposure goal, which means that we want to reach 45 million persons. Okay, so how do we write? We reach 4 million by using 1 minute of radio advertisement. So 4 times x1 gives you the total number of persons that you reach with radio. And this gives you the total number of persons that you reach with TV. And we want this, in fact, to be greater than or equal to this 45. We want to exceed this value. We don't want to deviate. We don't want negative deviation. Okay, negative deviation is problematic for us. But besides this, even this constraint was less than or equal to, greater than or equal to, or equal to. In order to convert it to a goal programming formulation, we include two deviational variables. Okay, negative deviation with a plus sign, positive deviation with a minus sign, and we convert the constraint to equality. Okay, so this is the exposure goal, and as I said, what do we want to do? We want to minimize the negative deviation. Therefore, our first goal is to minimize this negative deviation. Okay, for the second one, the budget goal, we want approximately $100,000 the total budget to be. So always when you have a budget, you want it to be less than or equal to. Okay, so it means that if you exceed this budget, it's problematic for you. You want to penalize the positive deviation from this one. Again, 8 times x1 is the cost of the radio advertisements, and 24x2 is the cost of the TV advertisements, and we include two deviational variables, negative and positive deviations, and we convert it to equality. And as I said, we want to penalize the positive deviation. Therefore, our second goal is to minimize this positive deviation. Okay, so now we converted our soft constraints into goal programming type formulations. We kept our hard constraints as they are, and we included these 4 deviational variables into our formulation. And now we have two goals, minimize G1 and G2, And let's see how we can use the weighting method to combine these into a single objective. As I said previously, in order to use the weighting method, we need these weights. And where do they come from? The weights come from the decision maker. And in this example, the decision maker is the management of the agency company. And when we talk to them in this example, this management told us that this exposure goal is twice as important as the budget goal. So what does it mean? So deviating from exposure goal by 1 unit is 2 times important than deviating from the budget goal by 1 unit. Basically, it says that if you are using a weight 1 for the budget, okay, then you should use a weight of 2 for the exposure. Okay, if you like, you can use different weight, but the thing is the ratio of the weight for the exposure to the ratio to the weight of the budget should be 2. So you can use 1 for the budget and 2 for the exposure. You can use 10 for the budget as a weight and 20 for exposure. Basically, it should be the weight of exposure should be 2 times the weight of the budget. Okay. Then, using this information, we can combine these two goals as 2 times exposure plus cost. And for exposure, we want to minimize the negative deviation. And for the cost, we want to minimize the positive deviation, which means that our combined objective function is this. And when we use this model, the soft and hard constraints, the goal programming constraints that we formulated, and also the hard constraints that we formulated with this objective function, and when we solve it, we obtain this solution. Z is 10. Okay, be careful. This Z is the optimal objective function value. When it is 0 in goal programming, when Z is 0, it means that you satisfied all your constraints. None of your target values are deviating from in this optimal solution. But when it is not 0, it means that at least one of the targets is not satisfied. So in this example, we have 10, which is not 0. It means that at least one of the targets is not satisfied. Okay, so the radio and TV minutes are, for X1 it's 5 minutes for radio, and for TV it is 2.5 minutes. So let's see these deviational variables. S1 minus is 5 million person. Okay, what does it mean? This S1 minus represents the negative deviation of the first goal. So it means that our target value was 45 million. We want to reach at least 45 million. But this says that we could only reach 40 million. And the deviation is 5 million, negative deviation. And it says that all the remaining variables are 0. Meaning that there is no deviation, positive or negative. There is no deviation for the budget constraint. We have exactly $100,000. We spent exactly that value. Okay. So you should keep in mind when Z is not 0, it means that at least one of the goals is not met. And in this example, the budget goal is not violated, but the exposure is violated by 5 million people. Okay, so this example is the last one that we will consider in this video lecture. We will talk about another approach to solve these problems, but the main idea in this weighting method, if we summarize, when we write these goal programming constraints, and when we write our goals, whether to minimize the negative deviation or the positive deviation, or negative plus positive deviations, from the decision maker, we need to obtain weights, the importance of the criteria with respect to each other, and then we use those weights to combine the objectives into a single one like this. And when we solve it, if the optimal z value is 0, it means that we satisfy all constraints. If it is positive, if it is not 0, it means that at least one of the goals is not satisfied. Okay, so this is all for today's lecture.